Welcome class to Chapter 8 on Hypothesis Testing Logic. Oh, here we go. So what is a statistic? It's, just basically an old way of mushing up our data. What is statistics? It's really the science of changing your mind under uncertainty. Statistics is all about making conclusions about the population, but testing the population isn't practical, right? Or feasible, so we test samples and make conclusions about the population. But what we know, our sample, is different from what we wish we knew, the population, and that's what it means to have uncertainty. So remember, statistics is the science of changing your mind under uncertainty. So what might your mind be set to do? Your mind is set to do, we don't like change, right? We like to do things as is, whatnot, until the evidence is so shocking that it says, really, you need to change your ways and do something else because look at this other way is much more profitable, better, or whatnot. So really, we use statistics all the time, okay? And that's what's so cool, I think, about studying statistics. So what might your mind be set to do? It's what I call the default action, the status quo, I've called it in other videos. And that's also known as the Null Hypothesis. That's a world where you are happy to stay with what you know and act according to the way that you have been acting, okay? And so to illustrate this with an example, let's say you own a business that sells mozzarella cheese. And you have a current marketing strategy that enables you to bring in X amount of sales per year. You do pretty well, but you're always interested in making some more money. And you pay people in the marketing department to help you figure that out, right? And so some people in the marketing department tell you that they can significantly increase your revenue, the money that you make, by creating string cheese, this new thing. So pretend in this world string cheese doesn't exist, and these people are saying, hey, we can make something cool called string cheese and it will increase your revenue. And it's just mozzarella, of course, but we'll package it in this little container and make it really cool, especially for kids. And pulling apart the mozzarella, I mean, how cool is that, right? So this change will require you, though, to spend more money to upgrade your factory, right? So this is an important action. This is a decision, right? In the real world, there's money involved, right? And you have to take actions, make decisions. So you decide, though, before you invest all this money into these upgrades, to see really if, come on, really, string cheese? I mean, isn't it mozzarella? Do you really think that lots more people are going to buy it and get super excited about string cheese? I mean, it kind of seems like selling a pet rock or something, right? Or sea monkeys, when I got all excited about sea monkeys and then realized they were just brine shrimp. So you decide to test this hypothesis to see if you want to change your marketing strategy and start selling string cheese. So your null hypothesis is your default action, remember? So you want to continue selling mozzarella and make X amount of money per year. That's your null hypothesis, right? So you start with that. And then you're wondering, hey, maybe I can make more money in this thing called string cheese. And that's your alternative hypothesis. That's the alternative action you'll take if the data tells you in your sample that, or samples, multiple experiments that you do, that your default action is ridiculous, okay? So remember that. An alternative action you take, the alternative hypothesis is the alternative action you take if the data tells you your default action, your null hypothesis, is ridiculous. The action to stop selling mozzarella and essentially start selling string cheese because you can make a lot of money, retire early, sell your factory, and live in Tahiti or Hawaii and sell shaved ice or something like that. So hypothesis testing and inferential statistics in a nutshell. Really, this is what it all boils down to is, does the evidence that we collected make our null hypothesis, our default action, look ridiculous? Say after me, does the evidence that we collected make our null hypothesis look ridiculous? Now you can't test the whole population of mozzarella cheese eaters. So you decide to take slices out of the population. Remember, you're taking little pieces of the population. You're hoping they're representative of the population, but there's no way of knowing, right? You're just taking a little piece. And test them to see if they prefer string cheese over mozzarella, right? So you ask the question, then after you get your data, does the data make you feel the default action, make your default action look ridiculous? If yes, then you reject the null hypothesis, default action of selling mozzarella, and make the conclusion in favor of selling string cheese, which is your alternative hypothesis, right? The data is so shocking, right? It's, oh my God, people just love this idea of string cheese, and it'd just be selling off the aisles or in the refrigerated section. If your data is not shocking, does not make your default action look ridiculous, right? Seems to fit within, it's, really not much of a difference between people's preference of mozzarella and string cheese, then you basically learned nothing. What did I say? Yes, say after me. You learned nothing. And instead of saying what they teach you, what they taught me in school, which I can't remember, and I will have to read word for word, is we fail to reject the null hypothesis and conclude that there is insufficient statistical evidence to support that string cheese increases sales revenue. Right? I think that's just a way to strain students' hands. Rather say after me, we learned nothing. Okay? Because we can't say that string cheese is worse or better. Right? We can only say that in this sample, the evidence did not support it. And there's no reason to change our mind that we should stick with the default. Is it the right action? Who knows? We can only say that we did our best to honestly analyze the data that we had in that given time with those samples that we did. Maybe we didn't test the right samples. Maybe the people that we grabbed, even though we randomly grabbed them, they just happened to be people that preferred mozzarella over string cheese. And we didn't make the changes. And we lost out on those millions of dollars that we could have made. To summarize, the game of hypothesis testing is all about determining whether the evidence that we have collected makes our null hypothesis, our default action, look ridiculous. Everything hinges on how we feel about changing our minds in light of the evidence. So the text then goes into talking about, of course, the online quizzes, and do online quizzes help students in their exam scores? Does it help better prepare students to take the exam? And the default action is keep doing as you've always been doing, right? And then the alternative action, that would be your null hypothesis. The alternative action is maybe incorporate these online quizzes. I want my students to be successful, right? So they look at, do the online quizzes help students perform better on tests versus past students who did not have the online quiz option? Past classes we'll use as the population, and the population mean right here, as you can see, is 75. The population standard deviation, the sign for that, is 3, and the current class mean, with the X with the bar over it, is 82. So at first blush, it would look like that 82 is pretty good, right? I mean, in terms of the standard deviations, I mean, heck, look. 75 plus 3, that's one standard deviation, is 78, right? And then 78 plus another 3, 2 standard deviations from the mean, right, is 81. So it looks pretty darn good. Statistical question, is the 82 a significantly higher score than the population mean of 75, showing that the online quizzes help students raise exam scores? So again, uncertain world, but we're trying to figure out with a certain level of probability that we might have found some error, right? That it is pretty helpful. Or did these scores occur by chance, had nothing to do with the online quizzes? And that's the statistical question. Whoa. So your null hypothesis, with the H and the sub-0 right here, notated, effect or relationship does not exist, right? The default action or status quo is there's no difference, no significant difference in the data between the online quiz students and the no online quiz students. So that's the default action, is no significant difference, right? And then the alternative hypothesis, are also called the scientific hypothesis. Mostly you see alternative hypothesis, which is signified by this symbol H sub 1. The hypothesis that an effect or relationship does exist. The data is going to make the default action look ridiculous, right? There's a significant difference in data. A score of 82 is a very rare score in the distribution of sample means. That is, of all possible samples of 30 students taken from the population, right? 30 students, samples, boom, 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 boom. Thousands of them that make up the population, right? A mean score of 82 is extremely rare. Okay. To find out if a significant difference, if online quizzes really help beyond chance occurrence, we need to look at the location of this mean in the distribution of sample means and see if it's a very rare score or if it belongs there and it's like not shocking, right? Does not make my null hypothesis look ridiculous. Not shocking. The general process for testing hypotheses using any statistics is to find the location of the sample mean in the distribution of sample means for that population and decide if it's an unlikely score in that distribution. If highly unlikely score, then the data makes the default action look ridiculous, right? So reject that null hypothesis and start selling string cheese, or start using online quizzes, or start taking caffeine to improve your memory, right? And we talked about in the caffeine study. And again, the distribution of sample means, book goes over this again, is a theoretical, just to refresh your memory, is a theoretical distribution that contains all of the sample means we would get if we were to draw all the possible samples of specific size from the population and determine each sample mean score, in this case, samples of 30 students who took the exams. Thus, the mean of the distribution of sample means equals, essentially, right, the population mean. Then the book goes over, but the standard deviation, a little tougher to figure out, right? Recall that variability, right, is affected by sample size. So when you see this, the Galton bean counting machine, I think it's what it's called, and they drop a bunch of balls here, and if you see that they don't drop that many balls, I've kind of posted some videos about this Galton machine. If they don't drop that many balls, you have a lot of variability, but as you drop the majority of them, or a bunch of them, right, then it starts to look like the normal distribution, right, and you have less variability. So recall that variability is affected by sample size, right? Increased sample size, less variability. Decreased sample size, more variability. And that the more scores that we have in our sample, the less variability we'll have in our data as the data becomes more representative of the population. Thus, the standard deviation of the distribution of sample means is based on the population standard deviation and the sample size. Okay? And if we know these values, we can calculate the standard deviation for the distribution of sample means, which is called the standard error. It's called the standard error when you know the population standard deviation. When you don't know it, it's a different thing called estimated standard error, but that's in a future chapter. But it's called the standard error. And you use the size of your sample because that's going to affect it, right, in terms of the variability. So I call it an adjuster sort of thing that fluctuates with the size of your sample. But anyway, the standard error, the estimate of the sampling error that's determined from the standard deviation of the distribution of sample means. The standard error represents how much we expect that sample to be different from the population. And like I said, it's an adjuster that fluctuates with the size of your sample, right? So if you have an increased sample size, that's going to change it. And so, of course, sample size matters. Once you get to 30, it's really, you're pretty stoked on that. That's a good number, as it talked about in the book. Next talked about the normal distribution, which is really an important concept for statistics because it allows us to compare the data from our sample to the population. And if the two distributions are similar, if they're both normally distributed, then we can really make easy statements about the likelihood that our sample data, for example, the online quiz students, came from the population, the default action status quo, students without the online quizzes, or if it was a very rare occurrence, right? So we can compare and contrast how common that score is, right? If the population distribution is normal, then the distribution of sample means will also be normal, and then we can essentially use the unit normal table to find the proportion of score in different parts of the distribution of sample means. Even if the shape of the population distribution is unknown or something other than normal, we can still determine the shape of the distribution of sample means using the central limit theorem. And what is that? It's a mathematical description of the shape of the distribution of sample means that states that for a population with a mean and standard deviation, the distribution of sample means for sample size n will have a mean equal to the population mean and the standard deviation equal to the standard error, and a shape approaching a normal distribution as n becomes very large. So essentially, in practical terms, you just want a sample of 30 and you're good to go, and the sample size as you increase will be more representative of the normal distribution and more like the population. Then the book talks about conducting a one-sample z-test. How rare does it have to be before we can decide that it probably doesn't belong in the sample distribution of means? The standard that we use in behavioral sciences for determining this is 5%. This means that there's only a 5% chance that our sample mean came from this distribution. So it's basically a cutoff score, as I'll talk about in a little bit here. If the percentage of scores for the sample mean z-score is at 5% or less for that score, then we can conclude that it is rare enough, for example, if it's in the critical region, it's rare enough for us to decide it's different from the sample distribution of means for this population. The book also talks about, which I'm going to go into in a little bit, the two-tailed test, which is very common for a two-tailed test, and that's what's right here. You might say, well, this isn't 5%, this is 2.5%, right? Well, there's 2.5 here and 2.5, and both together equal 5%. And I'll talk about the two-tailed test, but you're basically predicting it's going to go either this way or this way in terms of, sales on mozzarella or your alternative hypothesis, right? And so for a two-tailed test, instead of 5%, you want to use a z-score of 1.96, right? The magic number that I talked about earlier, which is 2.5%, right? So this way or this way. I look at it as kind of like crossing the finish line. Once you can get into this critical region right here, your alternative hypothesis is good to go. So the one sample z-test example, we know, and they're using, of course, this is the online quizzes example compared to no online quizzes. The previous population had a mean of 75, standard deviation of 3. Your current sample is 30, right? And your sample mean is 82. So you plug in all of these things and you get a pretty nice z-score. Looking up in the unit normal table, the proportion of scores above a z-score of 4 is only 0.003%, and yours is 12.73. So it's in a very extreme score, right, on the unit normal table. This tells us that the class mean of 82 is a very, very extremely rare sample mean in the distribution of sample means for final exam means in classes without online quizzes. So remember, the crux of basically statistics is, does the evidence that we collected make our null hypothesis our default action, right? No online quizzes, just continue as we've been doing, right? Look ridiculous? And the answer is yes, right? It does. It makes it look extremely ridiculous. It's way the heck over here. If yes, then reject the null hypothesis. The data supports the alternative hypothesis that online quizzes do improve exam scores. So next I'm going to go over the logic of hypothesis testing. And basically, it's a 5-step process. State your research questions and make hypotheses. Set a decision criterion. Collect your sample data. Calculate your statistics. And make a decision about the hypothesis. So before we jump into that, just a little overview of a couple terms in research design and in terms of how to infer causality. We reviewed research design in chapter 2 and 3. But you basically want to create equal conditions, right, for, let's say, two groups that you're comparing. And essentially, the two groups are essentially the same, right, with the exception of the manipulation of your independent variables. So I gave the example of testing caffeine, right, and whether it improves memory. So what we want to make sure we do is have the two groups essentially the same, except one group gets caffeine and the other group gets a placebo. It doesn't get caffeine. Original hypothesis is that there is no difference between the two groups, right? This provides us a baseline or a point of reference to measure if there is a difference, right? So this is why we start out with the statement that our null hypothesis is true. And we look at the results to see if the evidence proves otherwise. Okay. The other point I want to make is with statistics and your research is that we want to learn about the populations. Our hypothesis is about the population and not the sample, right? But we have to use samples which are not necessarily representative of the population, and that brings uncertainty, right? And statistics is the science of making decisions under uncertainty, right? Statistics is about taking actions in an uncertain world, right? And it does not create certainty out of uncertainty. Statistics does not create certainty out of uncertainty, but it gives us a way to make decisions and take actions that are backed by what the data shows us, right? If you stay with that, should we stay with what we have or do something else if the data makes staying with what we have look ridiculous? So step 1, state your hypothesis. The null hypothesis, effector relationship does not exist. The default action status quo. There's no significant difference in data between online quiz students and no online quiz students. You start off with the idea that the null hypothesis is true, right? All things being equal, we will stick with our default action unless the evidence is shocking, right? And sways us otherwise. And sways us to what? The alternative or scientific hypothesis. The hypothesis that an effect or relationship does exist, right? The data will make the default, if we get the data and it makes the default action look ridiculous, the alternative action must be taken. There is a significant difference in data. A score of 82 is a very rare score in the distribution of sample means. That is, of all possible samples of 30 students taken from the population, a mean score of 82 is extremely rare, which makes continuing with our default action, no online quizzes, look extremely ridiculous, right? So we reject the null. Step 1, you want to state your hypothesis. We're still on that, of course. And the alternative hypothesis, we're going to go over whether you're going to do a two-tailed or one-tailed hypothesis. A two-tailed hypothesis means both directions of an effect or relationship are considered in the alternative hypothesis. So in the example, you hypothesize that online quizzes have some effect. It will either increase the scores or decrease the scores. The null hypothesis in this example would be no significant effect. It will neither increase nor decrease the scores. Okay. In a one-tailed hypothesis, only one direction of an effect or relationship is predicted in the alternative hypothesis, right? So in this example, you hypothesize that online quizzes will have a positive effect. It will increase the scores. And the null hypothesis example would be no significant effect or a negative effect, right? So it's just going to basically cover this over here. And where the magic region, the critical region that you're trying to go for, is in this highlighted area. So that basically is it. Magic region for the two-tailed, if we go back to it, right, you're predicting is it could have a positive effect or negative effect. So the magic regions are here and here. Hopefully, obviously, you're right, you want them to improve, otherwise you wouldn't be doing the study, I'd imagine. And then the one-tailed, which is what you might go for in your study, you know, if you're really sure it's going to improve, you're looking for this magic region right here. So that brings us to step 2, which is to set the decision criterion. In inferential statistics, we are calculating a value that tells us the location of the sample mean in the distribution of sample means. The decision criterion value marks off a portion of this distribution that represents the most extreme scores. And this is called your alpha level. Okay? Your alpha level, marked by this sort of looking infinity symbol on its side, if you will, almost. This symbol right here is the probability level used by researchers to indicate the cutoff probability level, the highest value that allows them to reject the null hypothesis. So this is the cutoff right here, the finish line, right, for any scores that go in these areas allows us to reject the default action, the null hypothesis. I call it a risk tolerance knob, and a little more on that later, but basically where you set it is what you're comfortable with your risk. The critical region, the most extreme portion of a distribution of statistical values for the null hypothesis determined by the decision criterion. The critical region is basically these blue areas right here where you want your scores to be to support your null hypothesis, and for you to say, oh wow, that's shocking, that score of 82 is very shocking, it's an extreme score, it's in the critical region, right, and I can reject the default action, and I need to start incorporating online quizzes. This distribution of sample means corresponds to the sample means when the null hypothesis is true. Remember, we talked about that. If we find out that our sample lies in the critical regions, we can say that this is a very unlikely score to come from the default action, the status quo of the population, right? And so we can reject the null hypothesis, that default action, no online quizzes, and say that the data really supports the alternative hypothesis, which is that online quizzes help increase exam scores, right? So you make a decision about the null hypothesis depending on whether our sample mean is extreme for this distribution or not, right? Does the evidence that we collected make our null hypothesis, our default action, look ridiculous? Evidence provided by the inferential test is the chance of obtaining the data in the study if we assume the null hypothesis is true, right? We talked about that. If the probability of getting that data is extremely low, evidence clearly makes the default action look ridiculous, then the researcher takes that as evidence against the null hypothesis and rejects it. If the probability of getting that data is fairly high, the data seems to fit with the default action, it's not in those critical regions, then there's no evidence to reject the null hypothesis. You stick with the default, and like we said, you learned nothing. Step 3, you want to collect your sample data, design your study, test your hypotheses or hypothesis, recruit a sample, collect your data. These are the steps that we went over in chapter 2 and 3, for example, random assignments, sampling techniques, types of data, the NOR, right, nominal ordinal interval ratio, independent, dependent variables, and control of extraneous variables. Step 4, you want to calculate the statistics, and you want to figure out what statistical tests you will use. If we know the population's standard deviation, we will use a one-sample z-test. So this is a part of the flowchart. Remember on the huge, big flowchart, and we're comparing means, not correlational data, right? Correlation tests. How many sample means? We have one. Is the population standard deviation known? Yes. So we're going to use a one-sample z-test. And then we'll use the unit normal table in Appendix B to find the probability value, also known as the p-value. What is the p-value? It's a probability value associated with an inferential test that indicates the likelihood of obtaining the data in a study when the null hypothesis is true. I like to kind of call it the level of surprise, which makes the default action look ridiculous, or reasonable. Okay? If the p-value is low, you're extremely shocked. Oh my gosh, that's good, right? And the p-value low means that the likelihood of the null hypothesis being true is low. The evidence makes our null hypothesis our default action look ridiculous. So reject it and start selling string cheese, right? Or use online quizzes. If the p-value is high, your p-value output, you're going to get these p-values from your SPSS output. You'll find these very common. The p-value is high. You're not shocked at all, okay? The p-value is high means the likelihood the null is true is high. So stay with your default action. You learned nothing. In other words, you failed to reject the null hypothesis. If we do not know the population standard deviation, then you would use a new statistic known as the one sample t-test. We're going to review that in the next chapter, where you would use the estimated standard error, where S equals the sample standard deviation, and this is the symbol for the estimated standard error right here, S sub x with a line over it, and you'd use the sample standard deviation here. Yeah. And we'll figure that out, or we'll cross that bridge when it comes to the next chapter, right? And if you do not know the population mean, then you would do an independent samples t-test, okay? And then if there are more than 2 samples in a study, you'll use an ANOVA. So that's what's upcoming beyond the z-test. In each inferential test, we're using the same hypothesis testing procedure with 5 steps described in this chapter. And the same logic too. So the cool thing is, if you understand all the logic that I've talked about pretty much in terms of inferential statistics in this lecture, then the rest of the stuff's going to be pretty easy. Test statistic is a value representing the differences or relationships seen in the sample data, corrected for the chance differences or relationships that could be seen due to relying on samples. So you're correcting it with that standard error, and that's kind of what that means. Step 5, you make a decision. There are basically 2 decisions that you can make, right? Option 1, you find the evidence against the null hypothesis and reject it. And really, you're asking again, remember that basic question, does the evidence that we collected make our null hypothesis look ridiculous? Okay. So if you find evidence against the null hypothesis, online quizzes, online or sales of string cheese, and they are very extreme, right? Make our null hypothesis, our default action, look ridiculous. Then start selling some string cheese because there's people that love it. And then option 2 is you fail to find evidence against the null hypothesis and you retain it. Or as they say, you fail to reject the null hypothesis. The decision to reject or not reject the null hypothesis is based on the probability of obtaining the data in the sample when the null hypothesis is true. Remember, we talked about that. If the data is extreme, like our sample mean of 82, then there's a low probability that that data came from the status quo, default action of the population. Remember, it's in those extreme areas, right? And thus we can reject the null hypothesis and conclude that the data supports our alternative hypothesis, that there is a difference between the data in the 2 groups, and this is due to the online quizzes. That data does not belong. Step 5 again, continuing here, we compare the p-value with our alpha value. If our p-value is lower than our alpha value, for example, the p is lower than 2.5%, that is, our z-score is higher than 1.96, right? So higher z-scores, good, right? And that, of course, means our p-value is going to be lower, right? That high score, z-score, the exam score of 82 is extremely high score. Very low probability that that data came from the distribution of sample means. Reject our default action, the null hypothesis, right? It looks ridiculous, and support the alternative hypothesis. If our p-value is higher than our alpha level, then we retain the null hypothesis. So basically, if the p-value is in here somewhere, right, then you retain it. Types of hypothesis testing errors is what we're going to go into lastly here. And remember, the null hypothesis effector relationship does not exist, right? The status quo, your default action, sell mozzarella. No significant difference in the data between online quiz students and no online quiz students in that example. The alternative hypothesis and effector relationship does exist. There is a significant difference in the data. A score of 82 is a very rare score in the distribution of sample means. Of all possible samples of 30 students, taking the population, 82 is extremely rare, right? So we're going to either reject the null hypothesis or fail to reject the null hypothesis, right? Which brings up a common question. Why do we say fail to reject the null hypothesis? Why can't we just say that we support the null hypothesis? And in Europe, that brings up the whole tale of the black swan. In Europe for centuries, everyone thought that all swans were white. Essentially, the null hypothesis here would be the default action, right? All swans are white. Due to the fact that nobody had ever seen evidence to the contrary. Their sample, of course, was Europe. So people in Europe had never seen anything other than a white swan. But in 1697, a Dutch explorer found a black swan in Australia and brought back the feathers to prove it, which led people to reject the null hypothesis that there are only white swans. Now there are, that can't continue with our default action, white swans only, that there are black swans out there also. So just because we have not found evidence to the contrary in our samples, for example, does not mean that black swans do not exist. It means possibly that we just haven't found them yet, right? Okay. This is why we do not say that we support the null hypothesis, but rather say fail to reject the null hypothesis. As in this statement, we are keeping our options open that a black swan could be found in the future. So the types of errors in hypothesis testing are always possible, the errors in hypothesis testing are always possible because we're relying on a probability to make a decision. Okay, we set that alpha level, remember, and we're basically saying, did it cross that alpha level or not? The level that we set our alpha level to can increase or decrease the chances that we make different types of errors. Okay. Types of errors can be summed up as follows. Say a difference exists when there actually is none. Okay? And that's called a type 1 error, also known as a false positive. You're saying there is a difference between online quiz scores when there actually is none. And then the other one is to say no difference exists when there actually is a difference. And that's a type 2 error, also known as a false negative. In statistics, it's far worse to make a type 1 error, say there is a difference when there isn't a difference, than a type 2 error. Type 1 error. It's an error made in a hypothesis test when the researcher rejects the null hypothesis, rejects the default action, when the default action is actually true. We falsely say that there's a difference when there is none. And this is why it's called a false positive. Okay, we say, hey, there's a difference in the data when there actually is none. Okay. The chance of type 1 error is determined ahead of time by the researcher when the alpha level is chosen. An alpha level is the same as the chance of making a type 1 error. Remember, alpha level is a probability used by researchers to indicate the cutoff probability level, the highest value that allows them to reject the null hypothesis. It's what I call your risk tolerance knob. If you have a higher alpha level, if you set it at 0.10, you're going to have a more tolerance for risk. You're going to increase more scores that are kind of iffy into your critical region. They may not be as shocking as some of these scores of 82, right? You might start including scores that are like 77 or 78, right? As like evidence, right, to reject the null hypothesis. So you can see that your higher your alpha level means more tolerance for risk. You're okay with including scores that are less shocking, right? right? You're increasing your critical region, which means you're increasing your chance of a type 1 error, a false positive, saying there's an effect when there is none, right? You're increasing your chance of that. A type 2 error is an error made in a hypothesis test when the researcher fails to reject the null hypothesis when it's actually false, right? There's a difference, right? But you did not note it, and so you failed to reject the default. Okay. There are several factors that influence a type 2 error: the alpha level chosen, the size of the effector relationship, and sample size in the study. Type 2 error. Error made in a hypothesis test when the researcher fails to reject the null hypothesis when there is a difference. Okay, so you stick with the default action, but there actually is a difference. We say there's no evidence to reject our default action when there actually is, which is called a false negative. The evidence is shocking and makes our default action look ridiculous, but we fail to reject the default action. In this case, online quiz scores helped exam scores. Caffeine improved memory. String cheese increased revenues, but we continue with our default actions. No online quizzes, no caffeine, no string cheese. And we talked about those things, the several factors that influence type 2 error. Again, alpha level, it's our risk tolerance knob. Now let's take a look at it with type 2 errors. The lower the alpha level, 0.05 or 0.01, the less tolerance that you have for risk. It means what? You're shrinking that critical region down, right? And you only want to include scores that are what? Super shocking, that make your null hypothesis, your default action, look ridiculous, right? You want the super, super shocking scores like the 82, right? You don't want the 79 mean or the 78, right? And so you want the you only want to include scores that are super shocking that make your null hypothesis, your default action, look extremely ridiculous. And you have an increased chance of type 2 error, right? Saying there's no effect when there actually is, because you're only accepting those extreme scores. So hopefully that makes sense. Power is important, and you can test for power before you do your statistical tests. Essentially, it's the ability of a hypothesis test to detect an effect or relationship when one exists. So you can see this is closely related to type 2 errors, right? Detecting a relationship when one exists and not falsely rejecting it. Equals to 1 minus the probability of type 2 error. Anything that reduces type 2 error will increase power of the study. We already talked about that, right? Several factors that influence type 2 error. The alpha level chosen, obviously lower alpha level means less chance of type 2 error. The size of the effective relationship. So book didn't really go into this, but you can compare conditions, for example, that are markedly different to increase the size of the effect. For example, if you compared two types of meditation techniques on memory retention, you probably wouldn't have that much of a difference in scores. And it may not show you a stark difference between the two groups, right? But if you compared meditation with no meditation, or a task that was extremely annoying, right? You might have an extreme starkness in the difference of scores, and that stark difference in the scores is going to show you the effect, right, of meditation. And so that's what it has to do with the size of the effective relationship, is a stark difference in scores. And then the sample size of the study, as we increase our sample size, the sample becomes less variable, more like the distribution of sample means, which allows us to more reliably detect a difference when one exists. So you want to just increase. End result is you just want to increase your sample size to 30 to get good power. And that's the end of the video. Hopefully that was helpful.